All right, we're back at it, guys, going for the voltage and current division example number 2 that's in that packet that I gave you guys. So we're going to just go through and, just like we did in example number 1, take a look at how voltage can divide throughout a circuit and also how current can divide throughout a circuit. But first, things that we're going to be concerned with, we're going to be concerned with the voltage across the 25 ohm resistor, the voltage across the 35 ohm resistor, and the voltage across the 45 ohm resistor. But once we actually look at the nodes really quickly, I'm sure we can see that the voltage across the 45 ohm resistor will be the same as the 60, and we're also going to try to find the current through that 60 ohm resistor as well. So let's first take a look at the nodes and see what we can find out in terms of the relationship of each of these elements. So, yep, 10 volt source right here is connected directly to 20 ohm resistor by one point of contact. It means it's in series. What about this 25 ohm resistor right here? Well, it's connected to the 20 and also connected to the 35. You can see that that connection is the same over here because there's nothing in between the two elements. It's just a piece of wire. And right here, there's a node that separates the 35, 45, and 60. They're all connected here. So basically that point of connection, that's not series or parallel. It's just connected. Same thing with that one up here. And let's take a look. Yep. That point of connection is the same all the way across at the bottom. So 45 and 60, because they share those two common nodes, are definitely in parallel. So the voltage across the 45 ohm resistor is actually going to be the same as the voltage across the 60 ohm resistor. So in order to actually start determining any of these voltages, we need to actually collapse down the circuit into a single series loop. And so we're going to go through this step by step, and we're going to redraw the circuit as we go and make sure that we have a map so that we can go back and make sure that we can visually see where these voltages are actually dividing. So the first thing that we need to do is go ahead and put 45 in parallel with 60, and just as before, I say parallel by signifying basically two vertical lines here. So 45 in parallel with 60, that's 1 over the summation of the reciprocals. So 1 over 1 over 45 plus 1 over 60. And that combination comes out to be equal to 25.71 ohms. And just as I've said before in previous lectures, always go ahead and make sure that, one way that you can just understand that, that reasonably makes sense. Number one is because 45 and 60 are kind of close to each other, so there's going to be more of, I wouldn't say an even split by any means, but that number is going to make sense. And also, always know that anytime we combine elements in parallel, that the number that we get is always going to be lower or nearly equal to the lowest element in parallel, lowest value of that resistance. So let's go ahead and keep breaking down the circuit and make sure that we understand exactly how these elements will relate to each other. Well, once we combine 45 and 60 and gain that value of 25.71 ohms, that equivalence, that parallel equivalence between 45 and 60 actually now becomes in series with 35 ohms. And these two, that equivalence and also the 35 ohm resistor, that series relationship also relates to the 25 ohm resistor in terms of being parallel. If we combine these two together, that equivalence will become parallel with the 25 ohm resistor. Sure enough, to continue breaking down the circuit, 25 is in parallel with the series relationship of 35 and 25.71, so we just combine those two together. And sure enough, 1 over the summation of the reciprocals, we get 1 over 25 plus 1 over 35 plus 25.71. And so that combination, that parallel relationship that we see with 25 ohms and also these two elements in series now comes out to be equal to 17.71 ohms. So let's move the camera over and start talking about how these elements will actually start relating to each other. Now, as I've said before, parallel elements, they have the same voltage, different currents. Series elements have different voltages, the same current. But we're also going to see how that relates to equivalent resistance as well. Okay? Let's first find the voltage across the 25 ohm resistor. And in order to do that, we got to utilize that 17.7 ohms of equivalent resistance. So let's take a look. All right, so sure enough, once we actually broke down this into a single series loop, and let's just go ahead and show that sure enough all these elements are in series with each other. 10 volts is still connected to the 20 ohm resistor by one common node. 20 is now connected to the 17.7 ohms worth of equivalence by one node, and then 17.7 is sure enough connected to 10 volts. And we know that because this right down here, that is just a piece of wire signifying basically 0 ohms of resistance, just a piece of copper wire. So finding the voltage between these 2 points is easy. V1 is equal to V25. That's the 25 ohms of resistance that we were looking for at the very beginning of the problem. And that's also equal to the voltage across the equivalent resistance that exists between these 2 points. Remember that voltage exists between any 2 points within the circuit. But if we're the 10 volt source and we're personifying ourselves as the 10 volt source and we're looking in, we're not seeing that individual 25 ohms of resistance that we broke down in between these 2 points. It sees what drives that voltage is actually going to be that equivalent resistance looking in. It doesn't see 25, it sees 17.7 ohms worth of equivalence. Now, by voltage division, very simply, 10 volts multiplied by the proportion. Remember, it's directly that voltage is directly proportional to that 17.7 ohms of equivalence. So 10 volts times 17.7 over 17.7 plus 20 ohms. That gives us a value of 4.697 volts. So the voltage that exists between these 2 points here, sure enough, is going to be 4.697 volts. So that's the voltage not only across the equivalence, but also across the 25 ohm resistor that exists also in between these 2 points. So what we need to do now is go ahead and re-expand out. This is the reason why I say go ahead and redraw your circuit every single time. I want to see you guys doing that on the test. You should be doing that on your homework and also as you work through these problems. So going back and, I've redrawn this multiple times, even though we've drawn this before, just to make sure that it helps with the lecture and I don't have to keep moving the camera back and forth. But going back to the previous circuit before we broke it down to a single series loop, sure enough, here we got that 4.697 volts that exists between these 2 points. And that's also when we consider 35 ohms and the equivalency of 25.71 ohms. The voltage that exists between this node at the top and this node at the bottom, obviously we can see that that relationship shows parallel. That the voltage that exists between these 2 points right here is in fact also going to be 4.697 volts. But because we have 35 ohms and that equivalency of 25.71 ohms, because we have those two in series, that means that voltage will also divide again. So in fact, actually, V1 is not only just equal to the voltage of 4.697 volts, that's also, by KVL, also equal to V2 plus V3, the voltage across the 35 ohm resistor and also the voltage across that 25.7 ohms of equivalence. So all we have to do in order to get the voltage across each of these is just do voltage division again. So we take this 4.697 volts, and we go ahead and start dividing that again. So, but it only divides between 35 and then 25.71. And some of you may be wondering, well, why don't we use that 60 ohms right there? Well, remember that the voltage that's going to divide, if you have parallel elements because they share the same voltage, is going to be dependent upon that equivalent resistance there. So 4.697 volts, 35 over 35 plus 25.71, the ohms cancel out. So sure enough, the only thing that we got left right here is that proportion. And so here, 4.697 volts multiplied by the proportion directly proportional to 35 ohms, we get 2.7 volts. So the remainder of 2.7 from 4.697 should give us a value. If we just simply subtract that off, we could easily find V3, and it should give us roughly roughly 2 volts. See if that works with voltage division. So V3, that's equal to V60, and also that's going to be the same as the voltage across that 45 ohm resistor, right? So 45 ohms in parallel with 60, the voltage across both of those will be the same, and also will be the same across the equivalence of 25.71 ohms. So V3 is equal to V60, which is equal to V25.71. So 4.697 volts multiplied by 25.71 over 35 plus 25.71. Sure enough, that comes out to be roughly about 2 volts right there. All right. So if you guys have any questions on that material, shoot me an email. Let me know if this makes sense to you guys. We'll be discussing this obviously within the Microsoft Team meetings that we have. Now, these were just the voltages that we were concerned with dividing. So let's also take a look at that current that we were concerned with. That current we were really concerned with was the one that was flowing through the 60 ohm resistor. Now, could we just take 1.989 volts and just divide that by 60 and get that value? Sure enough, we could. But let's go ahead and actually do this by current division. And so what we're going to do is take the source current that we found right here. We're going to take that source current and then actually, well, we didn't find it yet. We're going to find that source current, and then we're actually going to see how that's actually going to divide throughout the circuit, just similarly how the voltages were dividing. Now, again, these are very, very simple. This one was actually a 3-loop circuit, but if we made like a 5-loop circuit, we could still perform these divisions very, very simplistically. It's just really understanding KVL and KCL and knowing those relationships of those elements and applying, the principles of those relationships, and then utilizing the tools that we have, such as voltage division and current division, appropriately. So you guys should not just be like working through these problems once. You should be working through it multiple times, and then also taking your understanding of this example and also the previous one and using that to work your homework. So let's take a look at how current divides throughout this specific circuit. So when we took a look at the source current, that was easy to find with that single series loop. That's just simply 10 volts divided by 20 plus 17.7 ohms. And sure enough, that came out to be equal to 0.265 amps. So if I wanted to find the currents here, let's just look at the currents and how they divide first. So IS, to make sure we understand where IS is coming from, it's coming from that positive terminal. So that's IS, but once it gets to these two parallel branches, 25 ohms is in parallel with the series combination of 35 and 25.71 ohms. That current of IS splits between I1 and I2. But look at this, we know 25.71, that was made up of 2 elements in parallel. So what happens is, if we look at the original circuit here, I2 flows through that 35 ohm resistor and then gets down to 45 and 60 and says, oh man, yeah, 45 and 60 ohms are in parallel. We're going to split again into IX and IY, which is what we were looking for at the beginning of the problem. We were looking for IY. But once they flow through those 2 elements and get down to this common node, they reform again back into I2, and then that I2 meets up with I1 and then reforms again back into IS and flows back into the negative terminal of the 10-volt source. So the first thing that we need to do is actually find I2. We're going to find I2 with current division now that we actually have IS, and that current, we're going to perform current division again to find the current through the 60 ohm resistor. So let's see if that works. So we took 0.265 amps, that's our source current, and by current division, remember we're looking for the current through these 2 elements here because they're in series. But we utilize with current division the opposite branch's resistance. So sure enough, we use that in the numerator, 0.265 amps multiplied by 25 ohms over 25 plus 35 plus 2.7 25.71. Ohms cancel out. Sure enough, we get a proportion. And that gives us 0.077 amps. So that's a current that's actually going to split. Again, 0.077 amps is flowing through the 35 ohm resistor and then splits between IX and IY. And sure enough, if we just find IX and IY really quickly, all we have to do is take that 0.077 amps, and that will divide between 45 and 60. So 0.077 amps for IX is 60 over 45 plus 60, the opposite resistance of the numerator. For current division, that gives us 0.044 amps. Should IY come out to be 0.033 amps? It should. Let's see if it works. IY is equal to 0.077. Opposite resistance goes in the numerator, again for current division. 45 over 45 plus 60, sure enough, comes out to be equal to 0.033 amps. All right, so that's example 2 in that packet that I have on eLearn for you guys. So if you guys understand what we went through with the first example and then what's in this video here, you should be good to go for test 1. But definitely make sure that you're continually practicing through these problems. Make sure you're doing your homework. Make sure you're looking at the practice test too, so you get more of an understanding of how I ask problems on a test. So if you guys got questions, again, come to me, send me an email. Let me know where you're tripping up on these problems, and we'll get those questions asked, get you solid, and then we'll be ready to go. All of this material, make sure you're really paying attention to it, because later on in the class, all this stuff is coming back. Basically, for our electricals, you're going to be holding on to this material throughout basically your whole entire career. So we really build upon concept after concept after concept, and you guys are getting the foundational tools that will allow you to do way more complex circuit analysis. So see you next time.